In this lab, we're doing lab 5, which is about user-defined convolution. In previous lab, we've already introduced the concept of convolution, but we've used the MATLAB built-in command or function for convolution. Today's lab, we're going to design our own user-defined function for that, and we're also going to introduce two additional concepts, which are the cross-correlation and autocorrelation. The three concepts of convolution, cross-correlation, autocorrelation are all related. If you understand the concept of each, you can simply only depend on convolution to extract the other two. For example, if you have two signals, x and h, and you're interested in finding the convolution between them, you can simply call the command conv in MATLAB. The cross-correlation, on the other hand, is defined as the convolution between x and h of negative n. That means you can simply flip h, the second signal, and convolve it with x. That will give you the result of cross-correlation. But there's actually a built-in command for that, which is named xcore. So you could either use xcore on h with on x with h, or you can depend on the convolution command and your understanding of cross-correlation to find the convolution using conv by simply calling conv x, flip lrh. The last topic, or the last concept we're introducing today, is autocorrelation, and it is defined as the similarity between a signal with a delayed version of it. That means you can simply call, or it is also defined as the cross-correlation between a signal itself. So you can either call cross-correlation function xcore on the same signal, so x with x, or if you simply give the xcore function just a single input, which is x, MATLAB will understand that you're interested in performing autocorrelation, so it will output it for you. Alternatively, you can use conv on x with a flipped version of x. So that means you're depending on your knowledge or your understanding of autocorrelation and how it works to figure out autocorrelation. So autocorrelation is defined as x convolved with x of negative n, and we understood that in MATLAB x of negative n can be created using x of flip lr on flip lr on negative n. This figure helps further illustrate the idea or the steps necessary to perform convolution. Assume we have two signals, x and h. On the right-hand side, you see signal h being flipped first. From here to here, we flipped signal h, and then we're shifting it along the other signal. And then at some point, you'll find some overlapping. Notice that once the first two elements overlap, you can figure out the length of your convolution. It will be length of the first signal plus the length of the second signal minus 1. Minus 1 is because of the first overlapping. We'll use this formula oftentimes in this video, and we've also have explained it during one of the lectures earlier. So going back to the concept of convolution, what you're going to do is shift the signal h after you flipped it along signal x, and then find out the overlapping elements, multiply them together, and then add the result of the multiplication. That will give you the convolution output. We are going to understand this further once we see actual examples on convolution. But this is just a recap on how to use the convolution function in MATLAB. You can simply call y, which is your output variable, and say that it is equal to conv f of g, assuming we're convolving signals f and g. Now we'll start with the first method to implement our own user-defined convolution function. The first method depends on using the formula for convolution. Initially, we can tell that we're going to need two for loops. The first one is to iterate through each element in the convolution result. The second for loop is for the iterator variable k. We're going to start by displaying a partially written code, and then we'll try to understand it and complete the missing part. The first line of code is part of the syntax for creating a new function in MATLAB. The function's name is myconv, as the built-in function for convolution is conv, so we just change the name so it will be unique. So now the function name is myconv. It has two inputs, x and h, which are the two signals we want to perform convolution between, and then it has one output, which is y, which is the result of the convolution. The first line of code inside the function is to compute len. Len is a variable that has the length of the convolution, and we already have mentioned that the length of the convolution is supposed to be the length of the first signal, so the length of x, plus the length of the second signal, length of h, minus 1. And we've already discussed why we need to subtract 1, and that is because of the first overlapping element. In the second line of code in the function, we're initializing y, which is the output, by allocating spacebar. We can already tell the size of y, and it is equal to len. So to initialize y, what we did here is actually creating an array of all zeros whose length is equal to len. So zeros is a built-in function in MATLAB that is used to create a matrix of all zeros of the provided size. So this is the number of rows in y, this is the number of columns in y. So now y is of size 1 by len. So this is the size of y, and it consists of all zeros. It's an array of all zeros, or it's a row vector, if you may say. In the next line of code, we're padding the signal x with zeros so that it will have the same size as y. It makes sense to just start with the for loops directly, but later on, once you compile your code in MATLAB, you're gonna run into errors, because at some point you're gonna try to extract elements of x or y, or h that do not exist. So you're gonna run out of indices. That's why later on you'll figure out that you'll need to add these two lines of code as part of the code. So here we're saying that x at index len is equal to 0. That means we're going to pad x with 0. So assume x is equal to 1, 2, 3. Then this line of code will just simply pad x with 0. So the new x is going to be 1, 2, 3, and then zeros until you reach the length of y. So the second part of the code that's missing requires us to pad the signal h with zeros, and it is very straightforward. We can simply copy the previous line, this one right here, and then replace x with h. So I'm gonna say h at len is equal to 0, semicolon, just to suppress the output so we don't see it. Now we're gonna move on to the nested for loops. The first for loop has an iterator named n, and we'll use it to assign values for each element in y. So that's why n starts at 1 and ends at len, which is the length of the signal y. The second for loop is to do the shifting for us. So here, y at n is equal to the current y at n. So initially, we've initialized y to be all zeros. So at the beginning, we're going to start with 0 here. and then we're going to add to it each time we enter the loop the next product result of these two numbers. So the missing part of the code we can tell is equal to x at k times, notice that MATLAB is case sensitive, so it's important that you follow the same guideline or the same case, or if you use lowercase k here, you need to be consistent with that. So now y of n is going to be equal to the current y of n, add to it x at k times h at n minus k, semicolon. Notice that the reason why I left space here, because I need to explain something before we finish the function. Notice that the first time you enter the loop, the value for n is equal to 1, right? And the value for k is also equal to 1. So that means n minus k is equal to 0. And it is impossible for us to access element at index 0 in MATLAB because the first index in MATLAB is equal to 1. I know in other languages the first index is 0, but in MATLAB the first index, or the index of the first element, is equal to 1. So to fix this issue, what we're going to do is we're going to add 1 here. This way we'll guarantee that the first time we enter the loop, we will extract h at 1, or the first element in h. This will help avoid having the error, the compilation error of saying indices must start at, or index value must be 0 or positive, or actually I believe the error message is index must be a positive integer and 0 is not a positive integer. That's why we're going to add a 1 here to fix that problem, or to avoid it actually. This concludes the first method for creating user-defined convolution. Now we're going to move on to a new method. This method is best illustrated using an example, and it's best used when you want to calculate convolution by hand. So assume we have a signal named x. Let's write down the sizes of each of our signals. For example, here we have x is of size 1 row by 4 columns. So this is the size. And h is of size 1 row by 3 columns. So assume you have two signals, x and h. The method states that you need to create a new variable named p, whose result is the product of x transpose and h. So this is like multiplication, but it's matrix multiplication. And remember, there is a condition for matrix multiplication that states that inner dimensions must agree or must match. That's why we took the transpose of t. This way, x transpose, the size of it is equal to 4 by 1. And the size of h is still 1 by 3. So now the inner dimensions are 1 and 1. And they do match, in fact. So that means matrix multiplication is possible. And the product will have a size of the outer dimensions, which is 4 by 3. So this is the first step in computing the convolution using the third method. The next step is to directly evaluate the output or the convolution result. This method states that if you have this matrix product, then the convolution is going to be, or the first element in the convolution is going to be the summation of the reverse diagonal matrix of the submatrix of size 1 by 1. So the first y of 1, or the first element in the convolution, is going to be the summation of reverse diagonal elements in the 1 by 1 submatrix. And similarly, y of 2 is equal to the summation of the diagonal elements in the 2 by 2 submatrix. If you're evaluating y of 3, then it's the result of the summation of the reverse diagonal elements in the 3 by 3 submatrix. So let's see an example here. Now we're evaluating the first element in the convolution. This is y at 1. Then the submatrix is going to be equal to 10, right? Just 10. If we sum the elements in the reverse diagonal, we end up with 10. So that will give you the value of the first element in the convolution. Next, we're going to look at the 2 by 2 submatrix of P, and then look at the reverse diagonal elements, which are 20 and 20. You need to add these two numbers together, which will result in 40. So that will be y at 2. So y at 2 is the result of the summation of the reverse diagonal elements in the 2 by 2 submatrix of P. Now when we evaluate the third element, if you want to evaluate the third element in the convolution, this is going to be the summation of the reverse diagonal elements in the 3 by 3 submatrix. So y3 is equal to the reverse diagonal elements in the 3 by 3 matrix. That's going to be 30 plus 40 plus 30, which results in 100, and so on. So we're going to repeat the process until you reach the last element in the matrix P. Notice that the size of the submatrix always increments. So it starts by 1 by 1, and then it's a 2 by 2 submatrix, 3 by 3, and so on. And then at some point, you're going to end up with another 3 by 3 submatrix, then 2 by 2 submatrix, then another 1 by 1 submatrix. So you can still start the coding using that algorithm or this method directly, but to make coding simpler, what we're going to do is we're going to simply change the size or the dimension of P, so it will always increment. So the submatrix size is always going to increment, and the way to do this is by simply padding the matrix P with zeros, like such. So it will have a size, it will have a square size, so it will always be incrementing. So we're always gonna have an incrementing size submatrix. So it will be 3 by 3, then 4 by 4, 5 by 5, and then finally 6 by 6. So from 1 by 1 until 6 by 6. This number is not random. This number is generated or can be calculated by looking at the length of the convolution itself. Notice here that the length of x is 4, the length of h is 3, and we said that convolution should have a length of y, or the convolution is equal to 4 plus 3 minus 1, or the length of x plus the length of h minus 1, which is equal to 6, which is exactly the number that we got here. Let's continue with the convolution itself. So the final element is going to be 120. Okay. In this slide, we see on the right-hand side the original matrix P, which was the result of multiplying x transpose with h. So this is actually equal to P, and P is equal to x transpose matrix multiplication, so there's no dot in there, times h. So this is how you write this code in MATLAB. And then here you see the same P after you pad it with zeros. And the way to do this is to find the length first. We said we need to evaluate len, and we know what len is. Len is equal to the length of x plus the length of h minus 1. So that means to generate this matrix, we need to say P at len, comma len is equal to 0. So we're going to display a partially written code and attempt on completing it. The first line of code is simply the function definition, y is equal to myconv x, comma h, and finally we have end to end the function. So this is all syntax for MATLAB. In the first line of code we are evaluating len, and we said len is equal to, I'm just gonna replace whatever is missing and write it here. So this is gonna be length of x. Let me erase this part. It's gonna be length of x plus length of h minus 1, and then a semicolon because you don't want to see the result of the length. And we've already explained this part of the code. This multiplies x transpose with h, and then here we're padding len with 0, and then we need finally a for loop to evaluate each element in the convolution. The for loop is partially written, but we're gonna start to understand it from scratch as if there is no code that's partially written for this part of the code. Notice what we were doing is we're finding the submatrices first. The first submatrix was consisting of this 10 by itself. So to extract this 10, what we need to find or type in MATLAB is P1, 1, right? This is going to be equal to 10. To extract this submatrix, what we need to type is P 1 until 2. So from the first row until the second row. So it's a range of indices. It's no longer just one index. It's a range of indices between 1 and 2. This is for the row number. For the column number, it's still 1 through 2, but we need to put it where we need to put the row number. So it will be the column number actually. So it will be 1 through 2. This is gonna give you the submatrix 10, 20, 20, 40. You might accidentally think that typing P22 is sufficient, but try to figure out what P22 will extract. P22 means give me the element lying at the second row, so here, and the second column, which is 40. So P2, 2 is going to simply output 40, which is not what we want. So this is not the correct way to extract the submatrix of size 2 by 2 from P, but rather this is the correct way to do it. For the 1 by 1 matrix, it was very simple because there is no other way to do it. It's from 1 to 1 and so on. Now we're going to move on to the 3 by 3 submatrix, which is this part of P. To extract the 3 by 3 submatrix, this is the 3 by 3 submatrix, what we need to type in MATLAB is simply P from 1 until 3, comma, from 1 until 3. So this will be equal to this submatrix highlighted in orange, which is 10, 20, 30, 20, 40, 60, and then 30, 60, 90, and so on. So you see a pattern here. it's always gonna be p at 1 until it starts at 1, then 2, then 3, and so on. The same as n. Starts at 1 until it reaches len, right? In this case, for our example, it starts at 1, 2, 3, 4, 5, 6. So it's always gonna end at len. So we're gonna say 1 through n, just like n, which is the iterator. It starts at 1 and it ends at len. So this is what we're gonna say to make our code generic, so it will work for any given inputs. So 1 through n, comma, 1 through n. So all of this work is just to extract the submatrix part of P. But then what we need to do with that submatrix is to find the reverse diagonal elements. We did an exercise in one of the labs that will help us extract the reverse diagonal elements, and we said we can simply flip the signal first, or the matrix actually. So to get the reverse diagonal elements, we're going to use flip first, flip LR, on, let's assume the matrix is named M, and then call diagonal on that, right? So we're going to apply the same concept here. I'm going to flip LR this part of the code. Let me erase it just to allocate more space for it. So it will be simply flip LR P 1 through n, comma 1 through n. So now this will flip the submatrices one at a time, and then what we need to do is to extract the diagonal of the flipped matrix. That means extract the reverse diagonal element. So we can simply call the diag function, right? Now what we need to do is to add the reverse diagonal elements together. So to do that, we're going to call the sum function. So sum all of this, right? Semicolon. And this will only give me y at n. So that completes the code for the second method for implementing our own user-defined convolution. Now we're going to start with the third method of implementing your own user-defined convolution function. This method depends on the concept of flipping the signal, the second signal, shifting it along the other signal, multiply the overlapping elements, and then sum the result of the product. So basically we're going to flip once, shift, multiply, sum, and repeat until we reach the end of the convolution vector or output. So here we're going to illustrate the concept using the same example from the previous slide. We have two signals, x and h. The signal we're going to flip is h. So in MATLAB, this is the same as saying that this is x. And the second signal is simply flip LRH. You can store it somewhere, for example, for us to be able to use it easily. FH or HF, for example, is equal to flip LRH. Notice that H is from the left-hand side 10, 20, 30. So when we flip it, it's now from the right-hand side 10, 20, 30. So the first step is to flip the signal and then shift it along the other signals. So we flipped H, we are shifting it now along X. N is going to be our shifting variable, and it's also the same as the index of the convolution output. So N is the shifting amount, and it is also the index number. So for shifting by 1, that means we're evaluating the first element in y. So shift by n results in evaluating y of n. So we've already covered how to flip the signal and how we do the shifting. Now to take care of the multiplication, we said we're going to multiply the overlapping elements. So far here, when the shifting amount is 1, we have 1 overlapping element in total. From x we have 10, from the flipped version of h we have, from x we have 1, from the flipped version of h we have 10. So we're going to multiply these two numbers. That will give us y of n, so the first element in the convolution. Now, in the next step, or the next iteration through the loop, we're evaluating y at 2, because the shifting amount is n is equal to 2. So that means we're shifting by 2, and we're evaluating y at index number 2. Now we have a total of 2 overlapping elements. These two together are overlapping with these two from the flipped signal h. So we're going to multiply 1 with 20, and then we're going to multiply 2 with 10, and then what we're going to do is sum the two numbers together. So that will take care of the summing part. So the result would be 40, which is equal to the second element in the convolution product, and so on. So we're going to repeat the process until we finish evaluating all the elements in y. So we just to recap, we said that we're going to flip the second signal once, so only do this once, and these two you're going to repeat n times, or until you reach the end of the convolution the convolution vector. So shift by n, multiply the overlapping elements, sum the result of the products when you did the multiplication. So we already have some part of the code written to implement this method. First part is to flip the signal, and then we also know that we need some sort of a for loop to iterate through each n, and we know that this for loop is going to stop at the length of y. So we can say that we need to say for example, n is equal to 1 through len, and then end the for loop. So this is also part of the code that we already know that is needed, right? And then inside the for loop, we need to figure out a way to perform the shifting, the multiplying and summing. So in the next slide, we'll explain this further. So in the previous slide, we've already explained some part of the code that's needed to implement this method. The first part is that we need to flip. We said we're going to need to flip the second signal. So we have x. We need to flip h. So let's store it in a variable named fh and name it, and then assign it a value equal to flip lr h. And then in this particular step or example, what we're doing is we have a shifting amount equal to 2. So n is our shifting amount, it's equal to 2. And we already learned how to take care of n, since this is going to be a for loop, right? For loop for n is equal to 1 until n, or the length of, until len, sorry, the length of our convolution. Now in this particular example, n is equal to 2, and what we're doing is actually we're multiplying each corresponding element between the vectors that have values equal to the first two elements, so first two elements in x with their corresponding elements in the last two elements in FH. So last two elements in FH. Notice that we're saying first two elements with the last two elements, and n is equal to 2. So we can generalize this and say that what we're doing actually is that we're multiplying element by element from the first n elements in X with the last n elements in FH. And we've already learned how to extract the first n elements in any vector. And we said the way to do this in MATLAB is to say X extract from the first until n, right? So this is a range of indices lying between 1 and n. But what we want to do is perform element-wise multiplication, because we are interested in multiplying 1 by 20, 2 by 10, and so on. So this is an element-wise multiplication. That's why we need the product here, the dot product multiplication. And then from FH, we want the last n elements. And then we said in one of the previous labs that the way to do this is to say end minus n plus 1 until end, right? So if n is equal to 1, for example, when you first enter the loop, n is going to be equal to 1. So what you're saying is end minus 1 plus 1, which equals to end. So you're taking the last element, which is what we want exactly. So all of this will help us do the multiply part of the algorithm, which consists of first flipping. Let me use a clearer color. So the first part is to flip, right? Then the shifting is being taken care of using the for loop. And then this is the multiply part. There is one last part in the algorithm which says sum. So to substitute for that, or to solve it, what we're gonna do is put all of this inside the sum function. So this will be step 3 and 4 combined. So let's look at the code. And it's also partially written code, but we've already completed it. Let's explain it and then try to complete the missing part together. We said, again, let me explain it one line at a time. The first line of code is the function definition. We've already talked about that. And in here we have the length of the convolution output. We said it's always going to be length of the first signal. Let me write it down. So this is going to be length of x plus length of h minus 1, semicolon. Then here we're padding each of x and h, in this case, with zeros so that they're equal in length, and their length is going to be equal to the length of y. So for here, what we're going to say is simply h len is equal to 0, semicolon. Here we're required to flip h, and we already have the code for that, and it's located here. And then inside the for loop, we're going to evaluate each element in y. That's why it starts at 1 and it ends at len. And we've already covered what we need to do for it. I'm just gonna rewrite it here so it's clear. We're gonna say that y of n, so each time we enter the loop, we're evaluating one element in y, is equal to the summation. So the algorithm says flip, right? Shift, and then multiply and sum are done together in one line of code. So we're gonna do the multiplication now. The first n elements in x dot multiplication, because we want to do element-wise multiplication, fh, the last n elements in fh, which can be found using the indices and minus n plus 1 until end. Don't forget to close all the parentheses that you've opened and then semicolon. So this will be the completion of this line of code. This concludes the third method for evaluating convolution using your own user-defined function. Now moving on to the last concept we're covering today, which is autocorrelation. Autocorrelation is simply the cross-correlation of a function with itself. So if you've defined your own cross-correlation, you can simply find the autocorrelation of a signal, for example, of x, using or by simply calling my x score on x with itself. Alternatively, you can simply call my conv on x with flip lr h. You notice that this is convolution, so it's convolution between x and flip x. That's why we use convolution on x with flip x actually, not h, because autocorrelation from its name means self, right? So that means there is only one input, so it's a correlation between a signal with itself. So it only takes one input, which is x, even though it's repeated, but it's still the same input. If you want, you can create a new function, name it, for example, my autocorrelation, that takes one input x. So you'll say function y is equal to, and then end the function here, and inside the function definition you'll evaluate y as either my conv of x with flip lr x, or using my x score, assuming you've defined my x score on x with itself. So this concludes the coding necessary, or the function definitions necessary. This concludes the function necessary for you to implement lab 5 of ELEG320. That concludes the lecture part of this lab. If you're live in the chat, please, and have questions, please ask away, either through the chat or using a mic. If not, you can always email me at aalatia@auk.edu.kw.